Hello, this is Mr. Mac. This is a video about classical probability, combined events, mutually exclusive events, etc. So let's get started. First of all, in classical probability, we talk about experiments. It's when we try to do something and we do something and there are different things that could possibly happen. Well, an outcome is defined to be the result of an experiment. So if we try an experiment, we do something happens, that's the outcome. Now the sample space is the set of possible outcomes. Now, I'm just going to mention here that we try to list the outcomes in such a way that they're all equally likely. See, if our experiment is rolling 2 dice, then the outcome of getting a 7 on the 2 dice is not as likely as the outcome of getting a 2 as the sum on the 2 dice. So in other words, when we do the experiment of rolling 2 dice, instead of saying the sample space is going to be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, what we do is we say, well, we're going to get 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 3, etc., etc., etc. And then those outcomes are equally likely. It's easier to come up with probabilities when the outcomes in your sample space, or you've listed your sample space in a way that the outcomes are equally likely. Now, an event is either an outcome or a group of outcomes. For example, if we were rolling 2 dice again, the group of outcomes might be that you get an even sum. Then it would be 2 or 4 or 6 or 8 or 10, etc., up to 12. So in other words, we can group some of the elements in the sample space together and call it an event. Now, we've got an example here, I guess, rolling an even number on a number cube. Now, the sample space, if we're rolling a number cube or a die, would be the set 1, 2, 3, 4, 5, 6. Now, the outcome that they've given us here, or the event that they've given us here, which is rolling an even number, would be the set 2, 4, 6. Now, probability, the probability of an event is the mathematical measure of how likely it is that the event will occur. Now, all of these probabilities have numbers somewhere between 0 and 1, because if you have an event, like say, let's say we're going to say our experiment is to roll a die, and our event is we're going to get a number between 1 and 6 inclusive, then that's definitely going to happen. And so we would say the probability is 1 or 100%. Now, if we say we're going to roll a single die, and our event is going to be we get a yellow tabby cat to take home. Well, that's not going to happen. We're going to get 1, 2, 3, 4, 5, or 6. So the probability of that event would be 0. That's something that won't happen. So on the continuum, a probability of 0 is something that won't happen. A probability of 1 is something that has to happen. The theoretical probability, though, just turns out to be the number of elements in the event divided by the number of elements in the sample space. Now we can make this a little bit cleaner if we just say the number of successes divided by the number of possibilities. In other words, we count up how many different ways we could be successful. We put that on the top. We count up the number of ways, the number of things that could happen. We put that on the bottom. And that is the theoretical probability of an event. Now, the next term here is the complement of an event. Now, the complement of an event is whenever you have a sample space, and let's go back to rolling a number cube or rolling a die, we'd have the numbers 1, 2, 3, 4, 5, 6. And let's say our event is we get a 1 or a 2. Well, now the complement of the event then would be the elements in the sample space that where the event didn't occur. In other words, in this case, it would be 3, 4, 5, and 6. And ordinarily, we will, if we have an event and we call it E, for example, then the complement of the event would be this little tilde in front of E or not E. Now, there's a couple of things to know here. If you know the probability of an event, then the probability of the complement of the event would be 1 minus the probability of the event. See, in other words, in these cases when we have an event and its complement, one or the other must occur. So if you want to know the probability of the complement of an event, you can, if you wish, subtract the probability of the event from 1, and that will give you that one. All right, now let's take a look at a couple of examples. Okay, first example, in a taste test, 50 participants are randomly given a beverage to sample. There are 20 samples of drink A, 10 samples of drink B, 10 samples of drink C. What is the probability of a participant getting drink A? Okay, well now, the probability of getting drink A would be the number of drinks of A, that's 20, over the number of drinks, 50, and that would reduce to 2/5. So the probability of getting drink A would be 2/5. Now the probability of getting drink D, ooh, you can't see this. There's 10 samples of drink C, 10 samples of drink D. So there are 20 of A, 10 of B, C, and D. That's probably not good. Well, what's the probability of a participant getting drink D? That would be 10 over 50, or 1/5, 0.2 if you wish. Probability of not getting drink C. Well, 40 of the drinks are not drink C, so the probability of not getting drink C would be 40 over 50, or 4/5. Now, since the probability of not getting drink C is the complement of C, it would also, the probability of not C would also be equal to 1 minus the probability of C. Now, the probability of getting drink C, we didn't figure yet, but still there's 10 of those. So we would subtract 10 over 50, or actually 1/5, and we would get 4/5. So that we end up with the same thing either way we do this. Now I need to get rid of this so that I can answer this next thing here. Now, experimental probability is the result of repeated experiments. A simple example would be if we flipped a coin 10 times, and let's say it came up heads 4 times and tails 6 times. Okay, so we flip a coin 10 times, and we get 4 heads and 6 tails. Now, the theoretical probability of getting a head when we flip a coin is 1/2. We expect that to happen 1 out of every 2 times. But when you actually do an experiment for a finite number of times, a lot of times the experimental probability isn't actually the same as the theoretical probability. In this case, the probability of getting heads, according to our experimental probability, would be 4/10 or 2/5. The probability of getting tails would be 6/10 or 3/5. That's experimental probability. Okay, now, second example. After receiving complaints, a skateboard manufacturer finds no defects in 502 skateboards. Let's say they inspect 550 skateboards at random. They find no defects in 502 of the skateboards. A, what is the probability that a skateboard selected at random has no defects? Well, that would be 502 over 550, and that is an experimental probability. Now, this is write the probability as a percent. To do that, what we would do is we would divide 550 into 502, and we get 0.913 as a decimal, which is the same thing as 91.3%. Now, part B, if 4,000 skateboards are inspected, predict the approximate amount that will have no defects. Well, we would expect 91.3% of the skateboards would have no defect. And you learned this, actually, I think before algebra. If you want 91.3% of a number, and in this case they gave us 4,000 as the number of skateboards, we would multiply 0.913 times 4,000, and that actually gives us something like 3,652 of the skateboards we would expect to have no defects. All right. Now, sometimes we have compound events. Compound events are events that say, okay, we're going to roll a die, for example, and we're going to flip a coin. Now, what's the probability of getting a number less than 3 on the die and a head on the coin? That would be a compound event. We would be doing 2 things. Now, we would be joining these compound events, the description of these compound events, with either the word and or the word or. Now, and means that both have to have occurred. And usually, in set theory notation, and is the same thing as intersection. If both have to occur, we use intersection. Now, or means that one or the other has to have occurred, or both, perhaps, either or both. And we use the symbol or the set operation union to deal with or. Okay, so when you're describing something with or, it's a union. When you're describing 2 events with an and, it's an intersection. Now, mutually exclusive events are events that do not overlap. That let's see, no. Let's see. The easiest way to say that is the 2 events cannot occur. The 2 events cannot occur at the same time. So if you have events A and B and they're mutually exclusive, you know that if A occurred, B didn't occur. You know that if B occurred, A didn't occur. Now, when the events are mutually exclusive and you want the probability of A or B, that turns out to be the sum of the probability that A occurred plus the probability that B occurred. Okay, so when the events are mutually exclusive, when they do not overlap, when the two events don't contain any sample space elements in common, then you just find the probability of each one, add them together. Now, in an IB school, example 3, there are 145 freshmen, 135 sophomores, 132 juniors, 115 seniors. A student is selected at random. Find the probability the student is a freshman or a sophomore. Now, first of all, we need to know the total of students here, and I think when you add that up, you get 527. So, well, let's just use that number, and if I screwed that up, I'm sure that you guys can tell me about that later. Okay, but if there's 527 total students, what's the probability that a student is a freshman or a sophomore? Now, if you're a freshman, you're not a sophomore. If you're a sophomore, you're not a freshman. So you see that being a freshman or being a sophomore are mutually exclusive events. That means the probability of freshman union sophomore is going to be 135 over 527 plus 145 over 527 plus 135 over 527. I looked up here, got them backwards. This is the freshman right here. This is the sophomores right here. So when we add them together, we get 280, I think, over 527. That might reduce. I don't think so. But the probability that a student would be a freshman or a sophomore would be 280 over 527. Now, if the events overlap, then you can't quite use this formula. But we do have a formula that works for this. And let's see if I can't illustrate this. Let's say, for example, you've got, and I'm doing a Venn diagram now. Here's a Venn diagram, and here's event A, and then here's event B. Now, it's pretty clear, I think, that the region here is where the two events overlap. I don't know what happened there. A moment ago, it covered the whole thing. This region inside, where the two circles are covering the same thing, that overlaps. Now, if this is the probability of A, and this is the probability of, well, let's see. We'll just keep this up. This is the probability of B. Can you see that this region right here has actually been counted twice? So what we do when the events are overlapping is we say the probability, oops, let's go back and get a different ink thing here. How about that? We say the probability of A or B is equal to the probability of A, that's the whole circle inside A, plus the probability of B, that's the whole circle inside B, minus the probability of A intersect B. You see, this region right here has been counted twice, so we take it away once. Now, this has a mathematical name. This is called the principle of inclusion-exclusion, but that's probably not something you're going to need to know for some time. Now, that would be how you handle combined overlapping events, or events that are not mutually exclusive. So here we have an example. A fair six-sided die is rolled. Find the probability that it lands on a prime number or an even number. Well, now the primes are 2, 3, and 5. And the even numbers are 2, 4, 6. So the probability of prime or even number is equal to the probability of prime, which is 3, 6. There's 3 of the 6 numbers are prime, plus the probability of even, again, that's 3 6, because again, there are 3 even numbers of the 6 that we could roll, minus the probability that it's both prime and even, and that's 1 6. So 3 6 plus 3 6 minus 1 6 is 5 6. So the probability of getting either a prime or an even number is 5 6. Okay, now I reject this next problem because you guys are IB students and the probability you're going to do your homework is much greater than 75%. Well, let's do it anyway. Okay, the probability that you will do your homework is 75%. The probability that you will listen to your iPod is 60%. The probability that you will do your homework and listen to your iPod is 50%. Find the probability that you will do your homework or listen to your iPod and draw a Venn diagram to display the situation. Well, let's start with the Venn diagram because the Venn diagram is going to help us a lot. It's always nice to have a picture. Okay, so let's make this circle represent homework. And we'll let this circle represent listen to your iPod. Now, the probability that you're going to do both is 50%. So that 50% goes right in here. Now, the total probability that you're going to listen to your iPod is 60%. Now, 50% of it is already in that circle, so there's another 10% for right here. The probability that you're going to do your homework is 75%. Now, 50% is already inside the homework circle, so there's 25% more to put in there. Now, this region out here, if we were to interpret it, this is that you will do neither. You will not listen to your homework. You will not do your homework. You will not listen to your iPod. And we can decide the percentage of that too, because the total percentage inside this rectangle, which represents the universal set of all the things that could happen in this situation, is 100. And so if we add up here, we've got 85% so far. So there's 15% more down here. So now, what is the probability that you will do your homework or listen to your iPod? Well, according to this picture here, it would be 25% plus 50% plus 10%, which is 85%. Now, these are all percents here. But if we use the formula, we would say that the probability you'll do your homework is 75%. The probability you'll listen to your iPod is 60%, and the probability you'll do both is 50%. So 75% plus 60% minus 50%. What is that? That's 135% minus 50%, which is 85%. So we get the same thing either way, okay, and that makes sense. Now we could also ask the question, what's the probability you'll do neither? What is the probability you will do your homework and not listen to your iPod? That's 25%. What's the probability that you will listen to your iPod and not do your homework? According to this Venn diagram, that's 10%. Okay, now you have an assignment to do on this, but this covers the basic things that you're going to need to know to do that assignment. So this is Mr. Mack signing off, and we're done.